Welcome back to another lesson on trigonometry. If you've been with me for a while now, you'll remember that we've obtained these exact values for sine and cosine from geometry and used trig identities to fill in the gaps. Here are listed some fundamental trig identities for your reference. In particular, I use the angle sum and angle difference identities to extend the previous table of exact values. There is certainly more than one way to do this, but regardless of which route you take, you'll find that 3 degrees is the smallest whole number increment for which you can find the exact values of sine and cosine. Go ahead and see for yourself. I omit the details, but you are encouraged to try this on your own and compare your answers to mine. Here the result of my efforts is displayed in table format. Notice the 3-degree increments. Whereas only sine values are displayed here for the sake of simplicity, remember that cosine theta is equal to sine of 90 degrees minus theta. So it is not terribly difficult to extract the information from what is provided. From the exact representation summarized in the previous table, it is possible to use basic algebraic operations, that is, addition, subtraction, multiplication, division, and square roots, to represent each value numerically in decimal form. This is shown in the table to the left of the graph. Think of the angle input as x and the output as y. These coordinate pairs are plotted on the Cartesian plane to the right. If the discrete points are connected, notice the result is a nonlinear curve. Our known values occur only at the dots. How do we find the value of an angle in between? That question brings us back to point-slope form. We can use any 2 points on this graph to approximate the values in between. As we shall soon see, there are better choices than others. First, we start with a line between 0 and 90 degrees. This is an exact approximation at the 2 endpoints, but notice there is a large gap in the middle. If we wanted to evaluate sine of 45 degrees, for example, using the yellow line, our answer would deviate significantly from the true value. Now we use 15 and 75 degrees as our points. The interval is now smaller. This is a better representation than the last one, but in the middle of the interval there is still quite a gap between the yellow line and the true values of sine. If we choose 30 and 60 degrees as the endpoints of our interval, the approximation is even better and the gap becomes smaller still. In the next lesson, we will examine sine of 58 degrees. This is bounded by the interval between 54 and 60 degrees, as shown here. If we zoom in, the red line represents our target of 58 degrees. Notice a small gap between the yellow line and the sine curve. What if we cut the interval in half and reduce it to 57 and 60 degrees? Zooming in and looking at the red mark, we see a negligible gap between the yellow line and the sine curve. They are virtually indistinguishable from each other at this level of magnification. In short, the closer our interval is to the target value, the better our approximation will be. That concludes this lesson. To see more videos like this one, consider subscribing to my channel. That way, you will receive notifications when I post new lessons. Also, be sure to utilize the comment section below for any questions or suggestions you may have. If you enjoyed this video and learned something new, please click that like button. As always, thank you for watching. I will see you next time.